In this lesson, we're going to talk about work done as energy transfer. We will interpret force-distance graphs, discuss power as the rate of energy transfer, calculate kinetic and potential energy, and we'll also look at calculations for how work is done with elastic energy. When talking about work, what is it? Work is the amount of energy that is transformed or changed when a force moves an object some amount of distance. Now we have to take into account two things. To say that a force is considered to have done work, the force must cause the displacement and the force must also be in the direction of the displacement. Here are some examples of work. We have a person who is mowing the lawn, he is pushing a lawnmower, and the force of the direction is in the direction that the displacement of the lawnmower is going. Another example is a horse that is pulling a wagon. Here, a person is pulling a little wagon with the kid inside too. Pushing a table is also doing work because you are moving the table a certain amount of distance and the direction of the force is in the direction of the displacement. When calculating work, the equation is the work done equals the force exerted in newtons times the distance moved. And we know distance is S. And the amount of work done is in joules, and we know that 1 joule equals 1 newton meter, also known as 1 meters per second kilograms per second squared. 1 kilojoule is a 10 to the 4th power, and 1 megajoule is 10 to the 7th. A gigajoule is 10 to the 9th. The reason why we use these right here, these prefixes, is because the joule is such a small amount that you might need to quantify it in a different way that's easier to write and better to represent. So here we have a person who has pushed the table this amount of distance in meters by this amount of force, and so therefore if we just multiply these two things we would get the amount of joules or the amount of work that was done. When you are doing work at an angle, so let's say you're pushing or pulling on an object, moving that object, but you're pushing at it at an angle, things will change a little bit. So we know that the equation is work equals the force times the distance displaced, right? Well, when you do this, we know that there's a y component and an x component when you have this force that is at an angle. We have this angle as being theta. This x component is the driving force that is acting in the same direction as the motion of the box. Therefore, we are going to be using the x component in order to solve for work. When we do solve for this x component, we know that the cosine of theta equals x over f, and the x is the x, this line right here. When we solve for x, we get f cosine of theta. So we know that this component is f cosine theta. So this is our equation when we're trying to solve for work that is done at an angle. Let me show you an example. A woman pushes a car with a force of 400 newtons at an angle of 10 degrees to the horizontal for a distance of 15 meters. To calculate how much work she has done, we draw a little diagram here to show us what we're working with, and we know that the x component is this black line right here. 10 degrees is the angle, and the force is 400 newtons. When we solve for this, we know that W equals F times S, which is the displacement, times cosine of theta, which then would give us an answer of 5,900 joules. Lifting objects is also an example of where work is being done, and that is because there is a force that is moving the object. The lifting force is equal to the weight of the object. We know that work equals force times distance. However, to show the distance as it's moving up, we are going to show this as being work equals mg, which is the weight, times the change in height, which is the distance moved. So it is the same thing as this. It's just showing that you're taking into account vertical movement and not horizontal movement. Okay, here is an example. A man lifts a mass of 120 kilograms to a height of 2.5 meters. How much work did he do? Given this equation, we also know a few things, right? So we're going to use this equation, and we also know that when lifting objects, the force is equivalent to that of the weight. We also know that the distance is the change in height, which is the delta H, which is 2.5 meters. When we plug this in, we are going to find the amount of force, which is the amount of weight. So when we solve for this, we just solve for weight, and that is equivalent to our force, which is 1,177 newtons. Now we can plug it in to solve for the amount of work done, and that is the force times distance. And when we plug in all of our numbers, then we get an answer of the work done is 2,942.5 joules, which after taking into account significant figures, we have 2,900 joules. We have graphs that are called force-distance graphs, and this shows how force varies with distance. This graph also shows energy losses that are due to air resistance, an object's speed, or the surface that the object travels on. What we do know, which is pretty cool, is that the area under the line tells us how much work has been done. Here are some examples. So if we have a force-distance graph here, and S equals the distance in meters, and force is in newtons, here we have the area, which we can solve for because it is a rectangle, and we know that that is the area equals the base times the height. If you're trying to find the area of a triangle, we already know that that is half times base times height. And of course, if you have a trapezoid, you have this area here. So all you would need to know is how to solve for area, and that would tell you how much work was done. For example, here is a force distance graph that is not as perfect and beautiful as the last two that I had shown you. Go ahead and try to solve what the area is under the line, which would then tell you how much work was done, and then start the video back up. All right, so I'm going to show you how I did it, and it might be a little bit more involved than what you have found, but I'm just going to spell it out very simplistically, and let's see if our answers come out to be the same. What I did was I separated this into three areas, and I'll call them A1, A2, and A3. And within these areas, I also know that I have a rectangle and a triangle, or two rectangles here, a larger rectangle in A3 and a smaller triangle. So I went ahead and just solved them by piecemealing them into either a rectangle or triangle. You might have done it differently, and that's totally fine. After doing everything, I solved for all the A1s. So I have a rectangle here, I have a triangle's area here. When I add that up, I get 30 joules. For A2, I got 40 joules, and for A3, I got 25 joules. So when you just add all of this up, this will give you the amount of work done, which was 95 joules. Power is another term that we use when we're talking about work, and it is the rate of doing work. In other words, what that means is it's the amount of energy that is changed per second. We measure this in watts. 1 watt is equivalent to 1 joule per second. The equation is that power equals the energy transformed, or the energy, the work that is done, over the time that it takes for that transfer of energy. If we have constant velocity, we already know that work equals the force times the distance, or the displacement. We now know that power is the work done over time. So if we take these two, we put them together, and we know that work done is the force times the displacement, and we plug that in for work done here, we get force times displacement over time equals F times distance over time, and we know that distance over time is the same as speed. However, when we're doing work, we know that the direction of the force gives the vector a direction, right? It gives it direction. Therefore, the speed becomes velocity. So we have power equals force times velocity, and we know that velocity is denoted by v. So that is the equation for power, for constant velocity. Gravitational potential energy, also known as GPE, which we've talked about before in the last video. It is energy that is stored due to its vertical position or height. It does depend on the object's mass and height. In order to find what the GPE is, it is denoted by delta E sub P, and the E stands for energy, the P stands for potential, and we have delta, which means the change in. So we have the change in energy of potential energy, which is denoted in joules, equaling the mass times the mass times gravity, right? So we have gravity here, and so that's the weight, times the change in height. Here is an example. A dog of mass 12 kilograms accidentally falls from an airplane at a height of 3.4 kilometers. How much gravitational energy does the dog lose between falling from the plane to the ground? All right. So here's a pictorial representation of our problem. We have the distance here as being the height. So the change in height is 3.4 kilometers, which is 3,400 meters. The mass of the dog is 12 kilograms, and we know that gravity is 9.81 meters per second squared. In order to solve for this, we just say GPE lost by the dog. So we want to know how much gravitational energy is lost. We solve that by plugging it into this equation here. And we get 12 kilograms times 9.18 meters per second squared times 3,400 meters gives us a loss of 400,248 joules. Kinetic energy, which we've also talked about in our last video. It is a form of energy which is just energy from motion. Objects gain kinetic energy when their speed increases, and it is denoted by the big letter E sub k, which means kinetic energy, equaling half times the mass times the velocity or the speed squared. This is when we assume that the initial velocity is 0 meters per second. If the initial velocity is not 0, then you use this equation down here, which is 1/2 mass times the final minus the initial velocity, and those two are each individually squared. Here's an example. A bullet of mass 150 grams is traveling at 400 meters per second. How much kinetic energy does it have? Go ahead and try to figure this out and then start the video again. So here's the answer. When we plug this in, knowing that the velocity is constant at 400 meters per second, we plug this into half, and then we know that the m is for the 150 grams, which we need to change into kilograms. We multiply that by the velocity or the speed squared, and we get an answer of 12,000 joules, because a kilogram meters per second, or kilogram meters squared per second squared, is a joule. So 12,000 joules is the answer of how much kinetic energy the bullet has traveling at that speed. When discussing energy changes between gravitational potential energy and kinetic energy, we can look at this ball, and it would be a great representation in order to describe what's happening on a kinetic and potential level. So at the bottom here on the left, we have the ball that's being thrown up and reaches a height where the velocity is 0, and then begins to come back down and reaches the same point at which it starts. At both of these points, what we have, actually let's look at the left side. We know at the left side, when the ball is pushed up into the air, that we can say that at this point that the ball is at its lowest point. And we know that potential energy increases as you increase the amount of vertical distance. Because it is at its lowest point, the potential energy is at its minimum. Whereas if it travels all the way up here to its highest point, its potential energy is going to be experienced at its maximum the most that it can possibly have. And then as it goes back down, its potential energy will be decreased again to the same amount, which is its minimal potential energy, because all of it has become kinetic. On the flip side, when you first start throwing the ball, we know that the kinetic energy is going to be at its maximum because it will be slowing down and changing back into potential at this point, and then speeding up to where the maximum kinetic energy is again at its highest point, right? So this is an example, a representation pictorially of energy changes between gravitational potential energy and kinetic energy. Here's another example of a pendulum. So it does not always have to be where the trajectory is a projectile. And so when we pull it here, it's parallel to the horizontal. And when it's at this point, this is the highest point that it is going to reach. Therefore, its potential energy is going to be highest here and lowest down at the bottom, where its kinetic energy is going to be the highest. And again, it just yo-yos back between highest potential energy to lowest potential energy, highest kinetic energy to lowest kinetic energy. Because acceleration is not constant, we cannot use Suvat equations when doing calculations. Here's an example. Just before the dog hits the ground, so remember that one equation where the dog was falling out of the plane, the numbers are still the same. So we have the data of the height being 3,400 meters. We have the mass of the dog being 12 kilograms. And we want to know right at this point before he hits the ground, how fast is that dog traveling? We can't use Suvat equations. So what we're going to do is, if you remember, we actually solved for GPE before, and we got an answer of 400,248 joules. We can now plug it into the kinetic energy equation, which is 1/2 times the mass times the speed squared. And the reason why we're using this is based off of that one picture of the ball that is thrown up in the air and comes back down to its starting point. We know that when the gravitational potential energy is lost, we know that the kinetic energy is gained. So it just transfers over. When we plug all of this in, we get 400,248 joules for the kinetic energy equals 1/2 times the mass of the dog times v squared, which is what we're trying to solve. And this part right here would actually become 6 kilograms times v squared. When we divide the 6 into the 400,248 joules, we'll get an answer of 66,708. And here are all of my units, which then my kilograms cancel out, and I'm left with meters squared per second squared, which of course, in order to solve for speed, we need to take the square root, which would then give us the answer of 258 meters per second. And that would be our speed of what the dog was going right before he or she hit the ground. Elastic or plastic energy. We did talk about this form of energy, and it is that materials can return the energy that has been stored in them when the force is removed. So it's showing here that now the spring is returning back to its potential energy. It has its same amount of energy, and that is a metal spring. But it is not the only kind of object that can do this. When you have, for example, instruments that you strum that have strings, a piano, a guitar, all of these objects return back to its former state and therefore has its original energy inside of it after it's been plucked or strummed. Here is the man who has studied springs extensively, and it is him, Robert Hooke, that we can thank for Hooke's law. What Hooke found out was that the extension or compression of a spring is directly proportional to the applied force, or also known as the load of the spring. It is denoted by this equation here. F equals the constant, which is the spring constant, measured in Newton per meters, times the distance of displacement, or the extension of the spring. The spring constant is different for each object. It describes the stiffness of the spring. The larger the number, the more stiff the spring is. Here is an example showing you a spring that has 100% potential energy. Over here, there is a mass that is put on the end of the spring, which is pulling down by some amount of force, which is equal to that of the spring constant times the amount of displacement that the spring moves. What we found out is that it takes twice as much force to stretch the same spring twice as far. And it is always multiplied by that constant, which is the letter K. Here's an example. A force of 600 newtons compresses a spring 0.5 meters. To find the spring constant, you would just need to plug in the force and the distance that it was displaced and solve for K. Here, in this case, it would be 1200 newton per meters. When we're trying to find the work done on a spring, it is the same as if trying to find the work done when there is a force that is applied to an object that is moved across a distance. So when we're looking at a force distance graph for a spring, it is the same. We find the area under the graph, and that will give us our work done. However, because it is a spring and there is a little bit of a difference, we do have to take into account Hooke's law. We know that work done equals half times the base times the height when we're looking for the area of a triangle. When we take into account Hooke's law, we do have to put in that the force equals the constant times the displacement, which then would give us the equation of W equals 1/2 kx squared, which this is the displacement squared. The new equation then would be the potential energy equals half times the spring constant times the change in x squared. Here's an example. A spring is stretched 60 centimeters and it takes a force of 40 newtons to hold it there. How much work did it take to stretch the spring to this point? The first step that we want to do is to list what we know. And we know that the force is 40 newtons and that the distance is 0.60 meters. Step 2 is to solve for K. We are given that the force equals the spring constant times the displacement of the spring. And when we solve for K, we get F over the change in X, which then when we plug everything in, we get 67 newtons per meter. Step 3 is to solve for work. We know that that is the potential energy equaling half times the K constant, the spring constant, times the displacement squared. Therefore, when we plug everything in, we should get an answer of 12 joules. All right, so that is everything. Be ready to use this information in class, and thanks for watching.